Have you ever stared at a big 6-mark exam question and just felt your brain totally freeze? Yeah, we've all been there. But what if I told you there's a formula for acing those questions? Today, we're going to crack the code on a real GCSE physics problem. I'm going to show you how to think like an examiner and grab every single mark. Ready to see how it's done? Let's dive in. Okay, so this is it, the big one, the 6-mark practical question. This is the kind of question that can seriously boost your grade. They're asking for a method, which sounds pretty straightforward, but the real trick is giving them exactly what they're looking for. It's all about getting inside the examiner's head.
All right, let's take a look at our little setup for today. It's a pretty standard circuit. We've got our power source, the cell, a switch to turn things on and off, and an ammeter to tell us how much current is flowing. Now, the star of the show is this piece of wire, held in place by these crocodile clips. And then, sitting over here in parallel, is the voltmeter, which is going to measure the potential difference or voltage across our wire.
So here's our mission. Describe a method. Basically what they're asking is, how can we prove that changing the length of a wire changes its resistance? This is where we need to lay out a really clear, step-by-step plan to make sure we don't leave any of those precious marks behind.
So how are we going to tackle this? Well, we're not just going to guess. We're going to use the ultimate cheat sheet, the official mark scheme. Honestly, this is the secret to success in any exam, knowing exactly what the person marking your paper actually wants to see. You see, the key to a perfect method is structure. We're going to break it down into 4 simple parts: setting everything up, taking the measurements, doing the calculations, and finally, a little quality control. Think of it like a recipe for getting perfect results. Let's kick things off with step 1. First things first, the setup. Now, the mark scheme is really specific here, and for good reason. You have to say you'll measure the length of the wire using the ruler. It seems obvious, right? But saying it shows you've actually thought about how you do it in the real world. Then, you have to state exactly how you'll change that length by moving the crocodile clips. It's all about being crystal clear.
Step 2 is all about taking our measurements. And again, being super specific is your best friend here. You need to explicitly state that you'll measure the current with the ammeter and the potential difference with the voltmeter. I know it feels obvious, but you have to write it down to get the points. Then, you tie it all together by saying you'll record these values for different lengths of the wire. Simple, but absolutely crucial.
All right, next up, a little bit of math. You've got your data, so now what? Well, you have to tell the examiner that you're going to calculate the resistance for each length. And here's a golden rule. Always, and I mean always, write down the formula you're using. In this case, it's V equals I times R. It's such an easy way to prove you know the physics behind what you're doing. And now for the final step, the one that really separates the good answers from the great ones: quality control. First, to make sure your results are reliable, you need to repeat your readings and calculate a mean or an average. That's standard practice. But here's the really clever bit. You should also disconnect the circuit between readings. Why would you do that? To stop the wire from heating up, which could totally mess up your results. It's that kind of attention to detail that gets you those top marks. Awesome! That's the 6-marker in the bag. Now let's move on to the next part of the question. This bit is all about visualizing our results and picking the right graph.
So which of these graphs tells the right story? Well, it's got to be the one showing a straight line that passes right through the origin, the 0, 0 point. This shape immediately tells a physicist that the relationship is what we call directly proportional. As the length goes up, the resistance goes up at the exact same rate. Let's unpack what that actually means.
This is a classic example of direct proportionality. Think about it like this. The more pizza you buy, the more it costs, right? And the price per slice stays the same. It's the same idea here. The longer the wire gets, the more resistance it has. If you double the length, you double the resistance. And it makes perfect sense that the line goes through the origin. I mean, 0 wire means, well, 0 resistance.
We're on the home stretch now. The very last part of the question is about safety, and it's a fantastic opportunity to scoop up a couple of really easy marks. Let's see what it is.
The question's simple. Why is using a 1.5 volt cell safe? Now, to get full marks here, you need to give a cause and an effect. The cause? The potential difference is very low. And the effect? Therefore, there is no risk of electric shock. You've got to state both of those parts to get both of the marks. And there you have it. We've completely pulled this question apart. So let's boil it all down into a simple checklist that you can use for pretty much any practical question. These are your key takeaways. This is your recipe for success, right here. Name your tools, like the ruler and ammeter. State your equations, like V equals IR. Explain how you're changing your variable. Talk about reliability and safety. If you can remember to do these 5 things, you're not just answering the question, you're thinking like an examiner, and that's how you get those top grades.
So, we've totally mastered how the length of wire affects its resistance. But, a good scientist is always curious. Looking at this setup, what else could we change? What other variable in this circuit could you investigate next? Have a little think about that. Thanks for joining me for this breakdown.